In this video, I'll be looking at the Gale-Shapley algorithm for stable matching. Firstly, we will look at the real-world problem behind the creation of the algorithm. During the 1940s, competition for medical students forced hospitals to offer internships increasingly early, sometimes several years before graduation. This meant that matches were made with employers before the students could produce evidence of their qualifications, and even before they knew which branch of medicine they would like to practice. Also, when a student decided to reject an offer made, it was often too late for hospitals to make a new offer to another candidate. Following this proposal, David Gale and Lloyd Shapley, two early 60s mathematical economists, proposed the question, could a college admission or job recruitment process be designed that was self-enforcing? What they meant by self-enforcing was that the process would enforce the outcome of each person based on their preferences, meaning that as long as each person was honest about where they wanted to study or work, then they would end up at the best possible place in agreement with the school or employer. It was issues like this that led to the formulation of the stable marriage problem. Generally, the stable marriage problem is stated as, given n men and n women, where each person has ranked all members of the opposite sex with a unique number between 1 and n in order of preference, marry the men and women together, such that there are no two people of opposite sex who would both rather have each other than their current partners. If there are no such people, all the marriages are considered stable. Well, in 1962, Gale and Shapley proved that for any equal number of men and women, you can always provide a stable solution to the stable marriage problem. Now, in order to show how the algorithm works, we'll formulate an explanation as cleanly as possible. And by cleanly, I mean that in some cases, when matching sets such as employers and candidates, there will be candidates looking for a single employer. However, employers might be looking for more than one candidate. However, here we're going to assume that we have n members in set A and n members in set B, and each member of A is only to be matched with one member of set B and vice versa. So, to denote the problem formally, consider a set of employers of size n and a set of applicants, also of size n. Let E times A denote the set of possible pairs between employers and applicants. A perfect matching S is a set of ordered pairs from E times A with the property that each member of employer and each member of applicants appear in exactly one pair in S and no more. Following this, each employer ranks each applicant in a preference list and vice versa. Employer E prefers A1 to A2 if A1 ranks higher than A2 on their preference list. Our aim is to formulate a perfect matching S where there are no two pairs, E1, A1, and E2, A2, where E1 prefers A2 to A1, and similarly, A2 prefers E1 to E2, meaning that the pair E1, A2 is much more optimal. So, how exactly does the algorithm behave during runtime? Initially, all employers and all applicants are unpaired. An arbitrary unemployed applicant A proposes to its top preferred employer E. As E is currently unpaired, the two enter an intermediate state as a pair EA. What we mean by an intermediate state is that we cannot assume that E and A will remain paired. There may be other applicants that rank higher on E's preference list that propose, and A would hence be replaced. Now that the algorithm has begun, we can assume that we have some free applicants and employers, and all others are in an intermediate stage. An arbitrary free applicant A proposes to the top employer E on their preference list, who they have not already yet proposed to. If employer E is also free, then the pair enters their own intermediate stage. However, if E is already paired with an applicant A2, then E determines which of A or A2 ranks higher on their preference list. Whichever ranks higher is paired in an intermediate stage with E, and the other becomes free again. Finally, the algorithm terminates once no elements in either set employers or applicants are free. All of the intermediate matches are declared final, and the resultant perfect match S is returned. To demonstrate the algorithm, take the following example. Here, we have 5 medical students, all of which have applied to take a year working at 5 different hospitals. Each hospital only has one more place for a graduate job and has ranked the candidates in order of preference. Now here you can see the preference lists of all the applicants and all the hospitals. To start the algorithm, we select Adam. As you can see, Adam prefers London. Moving to the hospital preference table, London is currently unmatched, so Adam and London become an intermediate match. Moving on to Ben. Ben prefers Newcastle. Newcastle is also currently unmatched, so Newcastle and Ben become an intermediate match. Moving on to Chad. Chad prefers London. Now, London is already paired with Adam, but because London prefers Chad to current match Adam, London and Chad become a match, and Adam becomes free. Moving back to Adam. Adam now prefers Manchester, because London is already taken. Manchester is also currently unmatched. Adam and Manchester become an intermediate match. Next up, Dave. Dave prefers Manchester. However, unfortunately for Dave, Manchester is already paired with Adam, and Adam ranks higher on Manchester's preference list than Dave does. So Dave moves on to preference 2, which is London. London ranks Dave higher than its current match, Chad. So Dave and London become a pair, and Chad becomes free once more. Now we get back to Chad. Chad prefers Newcastle. Newcastle prefers current match Ben to Chad, so unfortunately Chad remains free. Chad's third preference is Oxford. Oxford is currently unmatched, so Chad and Oxford become an intermediate match. Select Ed. Ed prefers Oxford. However, because Oxford already prefers their current match Chad, Ed remains free and moves on to his second preference. So Ed prefers Newcastle. Newcastle ranks Ed higher than their current match Ben. So Newcastle and Ed become a pair, and Ben becomes free once more. Moving back to Ben. Ben's second preference is Manchester. Looking at Manchester, Manchester is already paired with their top preference Adam, so Ben still remains free. Ben's third preference is London. London prefer Ben to their current match Dave, so Ben and London enter an intermediate state, and Dave becomes free. Selecting Dave. Dave prefers Plymouth as his second option. Plymouth is currently unmatched, so Plymouth and Dave become an intermediate match. There are no more applicants free, so the algorithm terminates, and the intermediate matches become final matches. An important thing to note about the process that we just ran through is that applicants were proposing to employers. However, historically, it's not always been the same. Before 2003 in the US, the algorithm was used by high schools in New York. However, because it was based on a school proposing system, around 30,000 students each year ended up at schools they had not listed on their preference list. At this point, Alvin Roth, a professor of economics, and his colleagues redesigned the algorithm based on a pupil proposing system. This reduced the students that were assigned to a school of no preference by 90%. The final thing I'd like to talk about is the time complexities of the algorithm. Let's take a look at this pseudocode that solves the stable marriage problem. If we look at the condition of the while loop, we can work out a worst-case runtime for the algorithm. Each iteration of the algorithm consists of a free man proposing to a woman for the first and only time. So using this, we can create a function pt in order to represent one iteration of the algorithm. Pt denotes the set of pairs mw, such that m had proposed to w by the end of iteration t. This means that for every proposal man m makes, another pair is added to the set. By this, we can deduce that for all t, pt plus 1 is strictly greater than pt. However, for each man m, there are at most n proposals he can make, bounded by the number of women. And there are at most n men. So, if n men make n proposals, we can say that the worst case runtime for the Gale-Shapley algorithm is of the order big O of n squared. I want to thank you for watching this video, and I hope it's been helpful.